The objective of this video is to introduce normal and reduced phase systems and the angular spacing of the voltage phasors of these systems. And this video is summarizing the results of Table 2.4 and Section 2.9.1 of your textbook. I want you all to please take some time and read this section. It's very brief. I'm highlighting here what are the important results for our development of fractional slot winding layout as we move forward, but please take some time and read these sections. So what this video is about, it's about considering your motor to have a different number of phases besides m equals 3. So we'll quickly summarize some results for windings from m equals 1, that's a single phase winding, up to m equals 6, a 6-phase winding. And I'm going to do this by constructing a table. In fact, this is the same table as is in your book, just without all the results. So you'll see that I've arranged this table to have columns, starting from the left side, where we're going to talk about the number of phases of any given motor. And then moving to the right, we're going to categorize it as either a reduced or a normal system. And the definition of a reduced system is that our number of phases is an even number. And the definition of a normal system is that our number of phases is an odd number. And so before we categorize it, we're going to draw a phasor diagram of what a non-reduced winding implementation would look like. And a non-reduced winding is a winding that has separate phases for both the positive and negative axes. So if we're talking about a motor with one phase, we would implement a non-reduced winding with a phasor diagram like this. And we'll say that this is m prime equals 2 because it has two windings. However, one of the phase windings is redundant. We don't need to have both a positive phasor and a negative phasor. We can just flow negative current to create the magnetic fields in that direction. And so when we reduce this down to a system that has the minimum number of phase windings, we will put it in one of these two categories. And since m is an odd number, we put it over here in the normal system category. And so you can see we would have a voltage phasor diagram that simply looks like this. And if we were to connect to this, if we draw the connection diagram for how the phase winding connects to a power source, very simply put, we would have one power source connected to our winding. All right, so this was the simplest case. The next case is a two-phase winding. And when we draw the non-reduced system, we again are showing both the positive and negative phasors because we have a phase winding for both positive and negative. And again, this is redundant. So we have 4 phase windings, but we actually only need 2. And in this case, this is called a reduced system because m is even. And so our phasor diagram would look like this for the reduced system. And if we talk about how we connect to it, we can sketch our coil groups, or our phase windings like this. And if we were, this is not the right answer, but hypothetically, if we were to try to connect to it without using the neutral point, you'd see that it's impossible. Any current that we would inject into this terminal has to flow out over here, and so these two current sources are incompatible. They would fight each other. And so the way that we actually have to connect to it is as follows. We would have to use the neutral point. And when you have to connect the neutral point to your power source, this is called a loaded star configuration. Your neutral point is also called your star point, and there's a load on it, so it's called a loaded star. Next, we'll categorize our system that we've been talking about all along, which is a 3-phase motor system. And so when we draw the non-reduced winding, we again end up with 6 phasors. And since m is an odd number, this is a normal system. And in this case, we do not need any connection to the neutral point. We can have a neutral point for the power source, which is independent of the neutral point for our load. And this is then called a non-loaded star. So as we increase our number of phases, a couple interesting things happen. Let's first talk about a 4-phase winding. So this will have 8 phasors. And this is clearly a reduced system because m is an even number. And here you can see how that would be distributed, and you can imagine how you would connect to it in a similar fashion to what we have above. We again need a loaded star. So you could draw a 5-phase connection. I'm going to just refer you to the book instead. What I want to draw for you is a 6-phase connection, or 6-phase winding. And then this is a reduced winding, so when we reduce it, we get a diagram like this. And what you'll notice is that if you select these two phase winding phasors and reverse them, that is, you rotate them 180 degrees, you can produce a radially symmetric phasor diagram. That is, a phasor diagram that looks like this. And this phasor diagram looks like two 3-phase windings that are rotated from each other. And so what you find is that you don't need to have a neutral connection to this star point. This is a non-loaded star. And it turns out, your book talks about this, it turns out that if your number of phases has an odd divisor, then you can arrange it as this non-loaded star configuration, which is advantageous. So this summarizes how we can categorize our windings based on whether m is an even or an odd number. But the real takeaway message that I want you to remember from this is the spacing that we have between these phasors. This spacing and this spacing. And you can see that it's different for the normal systems versus the reduced systems. And if we generalize this, for a normal system, our spacing is 2 pi divided by the number of phases. And for a reduced system, the spacing that we're trying to achieve in our phasor diagram is pi by m radians. So if we look at our diagrams up here, we can see that in this reduced system, we have pi by 2 radian spacing. In this normal system, we have 2 pi by 3 spacing. So in summary, this video has introduced normal and reduced phase systems. So that's the terminology here to describe a motor with an even number of phases is considered a reduced system, and a motor with an odd number of phases is a normal system. And then the video has derived or summarized the phase angle spacing in the phasor diagram for the winding. And this has implications for the design of our machines, because this is the phase angle spacing that we are trying to achieve when we use our star of slots to design a winding layout.